Hello everyone and welcome to today's theory prep video on recurrence relations. So today we'll be talking about a specific type of program called a recursive program. I'll explain what that is in a little bit and how to calculate the runtimes for it. In particular, we'll be focusing on the strategy of calculating runtimes using induction, although there are other ways to do recurrence relations and to turn them into explicit runtimes. We'll be focusing on induction in this course. Great, so what is a recursive program? A recursive program is a program that calls itself. So, for example, the Fibonacci sequence, for those of you who don't know it, is a sequence that starts 0, 1, and then from there, every number is the sum of the previous two numbers. So this would be 1, because 0 plus 1. Then here it would be 1 plus 1, which is 2. Here would be 1 plus 2, which is 3, 5, 8, and it just keeps going on like that. And so we could write a program to calculate the nth Fibonacci number, and basically what it would do is it gets some input, n, and then if n equals 0, well then it gives you 0 because that's the 0th number. Then if n equals 1, then it gives you 1 because that's the first Fibonacci number. And then otherwise, as we just discussed, the Fibonacci number is just the previous Fibonacci number plus the Fibonacci number that's 2 back. So it'll just calculate both of those things and it'll add them together. And this program is called recursive because the program Fibonacci calls Fibonacci again. So it causes this recursive structure. So this sort of gives us an interesting quandary when we're looking at analyzing the runtime of this program. So let t of n be the time to compute Fibonacci n. And I know in the last video we said like runtimes were expressed in the number of bits, but runtimes could be also expressed for like the actual input. So it really just sort of depends. That's a very flexible thing. And so t of n can be the time to compute the nth Fibonacci number. And we'd love an explicit formula, right? We'd love to know, well, this is a linear program, or this is a quadratic program, or this is an exponential program. But the program doesn't really give us that. If we had a non-recursive program and there was like a for loop here, and then the for loop had to go n times, and maybe it was O of n, or if there were like 2 for loops, then it might be O of n squared or something, and we could do analysis based on how many lines is it going to have to run. Well, then therefore it'll probably take this amount of time. But here we don't have anything like that, and in particular we have this problem because the Fibonacci function or the Fibonacci program might call the Fibonacci program again, in which case our expression for t of n is really going to have to be in terms of t of n minus 1 and t of n minus 2, right? So if we look at how long this program is going to take to run, these first 4 lines, well, that'll just take some like constant amount of time, right? And it might return before then. But in the worst case, it's going to continue all the way down to run through everything. And then it'll have to call Fibonacci on n minus 1 and Fibonacci on n minus 2. And then it's going to take some more constant amount of time to like add those two things. Usually in most cases in programming, you just consider adding to be a constant time operation. There is sometimes you can do analysis of like time to add numbers and stuff, but in this case, we'll consider that a constant time operation. So all of this, like these first 4 lines and this plus, like we can do all of that in some like constant amount of time. Let's call it big C. So that allows us to write at least some sort of relationship, right? The time to calculate the nth Fibonacci number, well, in the worst case, it's got to do all of these operations, like all of these if statements, and so that'll take some constant amount of time, big C. And then we might also have to call Fibonacci on n minus 1 and Fibonacci on n minus 2. And remember, t of n gives the time to compute Fibonacci n, so that'll just take time t n minus 1 and time tn minus 2. So we'll add those things together, tn minus 1 plus tn minus 2 plus this constant c amount of time. But this isn't particularly helpful because it doesn't really tell us anything about how, well, it tells us a little bit, but it doesn't give us an explicit formula for how long it will take to compute the nth Fibonacci number. And that's not great. So what we're going to spend the rest of the time doing today is taking this, which is called a recurrence relation, because it expresses a runtime in terms of itself, just like how a recursive program calls itself. And we're going to turn that into an explicit relationship. So I claim that t of n is big O of 2 to the nth. That's what we're going to prove. And in general, a lot of the time, we're more concerned with big O than big omega because we're trying to prove it runs in at most this amount of time. So, we know it's at least this efficient. We care less about, what is the fastest possible time that it could run in, and more upper bounding how long it might take to run. So remember to review the definition of big O. That means that there exists some n and c in the natural numbers such that for any n greater than big N in the natural numbers, t of n is less than or equal to c times 2 to the nth. So we have to choose, the first thing we do is choose big N and c. So we'll choose big N equal to 0, and we'll choose little c equal to big C, where big C is this constant from the recurrence relation. And now we're going to prove for any n greater than n, any little n greater than or equal to big N, the natural numbers t of n is less than or equal to c times 2 to the n. You'll notice that technically we only have to prove for any n strictly, but here we'll just prove for any n weakly, and that's going to be better. It'll also help us sort of with our induction. So, well, I guess I just gave it away, but we're going to proceed by induction. We're going to, as when you have statements for all natural numbers, induction is a great way to go. So we need to do two things for our proof by induction. First, we need to do the base case, and there's actually going to be two base cases. So the first base case is n equals 0. So we want to show, to be explicit, we want to show that t of 0, so the runtime to compute the zeroth the zeroth Fibonacci number, is less than or equal to c, which is little c is big C, so big C times 2 to the 0th, right? Which is equal to showing that it's less than or equal to big C. But we know that that's true because if we run Fibonacci 0, it'll go to this if statement and then it'll just return 0. And big C is the upper bound on all of these additional operations aside from looking at Fibonacci. And so we know that t of 0 will take less time than all these extraneous operations because it just does a subset of these extraneous operations. So this checks out. Similarly, for base case n equals 1, we want to show that t of 1 is less than or equal to c times 2 to the 1th just equals 2c. And again, this makes sense because, well, what happens when we run this on 1? Well, it checks this if statement. Well, that's not true. It checks this elif statement, and then it goes ahead and it returns 1. So it's just running 3 of these extraneous lines. So the runtime must still also be less than c, which therefore will be less than 2c. So this statement also checks out. So now we've shown that our statement tn is less than or equal to c times 2 to the nth is true for 0 and 1. So now we want to do the inductive step for n greater than or equal to 2. So let's write out what we want to show. So we want to show that t of n plus 1 is less than or equal to big C times 2 to the n plus 1. Great. And we'll use a recurrence relation for this. So t of n plus 1, going back to our recurrence relation, will be less than or equal to t of n plus t of n minus 1 plus c. So let's write that out explicitly. T of n plus 1 is less than or equal to t of n plus t of n minus 1 plus c, right? And this first part comes from, well, you might have to calculate the previous Fibonacci number. Then you might have to calculate the Fibonacci number 2 back, and then there's the constant c of other operations that you do in the program. And so, but we know by our inductive hypothesis, right, that this first thing is less than or equal to big C times 2 to the n. And we know the second thing is less than or equal to big C times 2 to the n minus 1. So we can substitute that in. Let's write this a little bit more clearly. 2 to the n minus 1 plus the last term is big C. And so the next thing to note is that since n is greater than or equal to 2, this implies that 2 to the n minus 1 times c is greater than or equal to c, right? Because in particular, this n greater than or equal to implies 2 to the n minus 1 must be at least 2, and 2c is greater than or equal to c. So this is less than or equal to c times 2 to the n plus c times 2 to the n minus 1 plus c times 2 to the n minus 1. And this last term just comes from this inequality that we just said. And then we have 2 copies of c times 2 to the n minus 1, so that just gives us 2 to the n times c. And then 2 copies of c times 2 to the n gives us c times 2 to the n plus 1. So now we've shown that t of n plus 1 is less than or equal to c times 2 to the n plus 1. And that completes our proof. Because if you recall, what we were trying to prove is that for any n greater than big N, right? So for any n greater than 0, because we chose big N equal to 0, t of n is less than or equal to little c, which is big C, as we defined it, times 2 to the n. So that's how you can take a recurrence relation, that doesn't necessarily tell you anything explicitly about how long something takes to run, and you can turn it into an explicit formula or an explicit asymptotic relationship. I think the other thing that I wanted to talk about is, how did I know to choose 2 to the n? So that's a great question. And sometimes you just sort of have to guess. In this case, let's think about what happens when we run Fibonacci of n. And I'm just going to write n for running Fibonacci of n. Well, that'll cause us to run Fibonacci of n minus 1 and Fibonacci of n minus 2. Fibonacci of n minus 2 will cause us to run Fibonacci of n minus 3 and n minus 4. And Fibonacci of n minus 1 will cause us to run n minus 2 and n minus 3. And you'll see that each of these essentially has 2 branches off, and so basically it's going to take an exponential amount of time, because as you guys proved last week or a couple weeks ago in the graph theory p-set, this binary tree will have basically 2 to the n leaves in the worst case, and this will be the worst case, almost. At the end, it'll sort of start getting truncated, but still, it's not much better than exponential, and so that's sort of the bound that we're going to put on it.